All right, so I've got 6:02, so I think we can probably get going now. So hi, everyone. Thanks for joining us today. My name is Tommy, one of the co-organizers of Data Science DC. This month, we actually have sort of a special event that has been put on or supported by 4 different organizations. So you've got Data Science DC. We also have the Text Analysis Interest Group of the American Statistical Association, the Washington Statistical Society, and then we got a nice bump from Seth Grimes, who runs all 3 of DC Natural Language Processing, New York City Natural Language Processing, and Philadelphia Natural Language Processing. So looking forward to the collaborations here. So this is Data Community DC. For those that have not come to a Data Community DC meetup or Data Science DC, Data Community DC is an umbrella organization for about 9 different meetups in the Washington DC area that's all related to data science-y type stuff. Here are the logos of several of our meetups here. We got a website, datacommunitydc.org, where you can get see our blog, see the calendar of events, and sign up for our newsletter. We also tweet at Data Community DC on Twitter. 3 co-hosts for Data Community DC, Maria Gander, Tommy Jones, that's myself, Jeff Hale. You can follow all 3 of us on Twitter if you'd like, or send us an email at our Data Community DC email. I'm Thomas, THOMAS, at datacommunitydc.org. Jeff is Jeff at datacommunitydc.org. I don't think Maria is with us right now, but she's M. Gander at datacommunitydc.org. And I'm also the webmaster of the Text Analysis Interest Group. We formed recently. We've got 3 goals, but I know Kelly is in the audience here. She is our chair, and I wonder, Kelly, if you wanted to say a few words, or if you'd like me to take it.
Hi, everybody. It's Kelly Zoe. Thank you, Tommy, for hosting this joint session. I think this will be a fantastic feature, because this is one of our student winners from last year. So hopefully you'll enjoy it. And then, as Tommy said, Text Analysis Interest Group, even though this is with the ASA, we do welcome any members who are non-ASA, those who are interested in text analysis. So just contact Tommy, if you're interested. And then also we have our chair-elect, Dave, in the audience. So thanks so much for joining tonight.
All right. I'm personally very excited about the Text Analysis Interest Group. Oh, and David, I see you've joined. I don't know if you wanted to say hi.
David Banks. I just want to say hi to everybody and thank you for turning out. It's going to be a great talk.
Looking forward to it. So we do have a code of conduct. We're dedicated to providing a respectful, harassment-free community for everyone. We don't tolerate harassment, bullying of a community member of any kind. What I would say is that, to paraphrase this slide here, is if you are being harassed, if you witness anyone being harassed, either during the meeting, like in an individual chat, or maybe afterwards or on the community board or anything, reach out to Jeff or myself. That's Jeff at datacommunitydc.org, Thomas at datacommunitydc.org. And we will intervene on your behalf because we don't tolerate that sort of behavior. Mostly it's a good community. We have had to take action before, and we won't hesitate to do so. But we do love that, by and large, everyone treats everyone else with respect. We also have a diversity statement. So if this was a year ago and we were still live, this would be the moment where I would ask everyone to look around the room and realize that everyone in the audience has a significant amount of racial, ethnic, and gender diversity. And so our pledge as the organizers here is that we want our speakers to reflect the diversity of the community. And so, you know, part of this is cultural, and that's something that's a community aspect. Please be inclusive, include everyone. We don't want anyone to feel left out. But also, again, as our pledge to you, if you feel like we are not doing a good job, let us know and we will fix it. But we especially want to provide this place as a forum for folks that may be otherwise underrepresented in the community, particularly as it relates to, say, prestige and power. These are our sponsors. Again, in the before times, we would be thanking them for pizza. In the now times, we will thank them for our Zoom license. ATA and Snorkel. Snorkel AI are our two premier sponsors, and then we also get some financial backing from Science Logic, Statistics.com, Excella, and Neo4j. We really can't hold these events without these sponsors, so I would ask everyone to take a look at these organizations and see if there's anything that they could do for you. And look forward to getting back in person again and having that pizza someday. So community announcements again, normally we'd go around the room, but just a few that I will announce. So in a couple days, Statistical Seminar DC is going to be holding an Intro to R meetup. You can Google Statistical Seminars DC and it will, their meetup page should be your first result. Ditto for Data Visualization DC, Thursday, March 11th. They haven't announced the topic yet, but they do have it scheduled. And then on Tuesday, March 2nd, DC NLP, which is not technically part of Data Community DC, but we're very close friends. They're going to be hosting a meetup, Transformers to Rule Them All, under the hood of the AI Recruiter chatbot. And so that'll be a pretty good time too. And so with that, Queenie, I'm going to stop sharing my screen and turn the floor over to you. Okay. I will say for the audience that I saw Queenie present at the Joint Statistics meetings over the summer, and she was fabulous then. So I think you're all in for a treat.
Thanks.
Oh, and while we're waiting, a last process note. If you have any questions, feel free to drop them in the chat, and then afterwards, we'd be happy to ask those questions of Queenie.
Yeah, I'm sharing the screen. It just takes a little bit of time. Today, my laptop is extremely slow somehow. Oh, okay. Am I sharing now?
I have a notification that says you've started screen sharing, but nothing's come across yet.
Oh, okay. Maybe wait for a couple seconds.
Yeah, if anyone has other meetup announcement, maybe put that in the Slack channel, or if you're looking for something, if you're looking for jobs or hiring or anything, like this is a good time to share anything that you any community announcements you might have or personal announcements.
And also, Queenie, if you want, you could also try and email me your slides, and I can run them too if we think we're going to run into an issue here.
Yeah, that's also a good idea. Yeah, it shows me currently sharing, but I guess maybe I should email you.
You are sharing now.
Yeah, I can see it now. Give a thumbs up in the chat there if you're seeing it.
Oh.
Yeah.
Yep. Yeah, it just came up for me as well.
Oh, okay. Okay. Cool. So my talk is about text mining and music mining. And yesterday I added a subtitle as an internal golden braid, and I will explain this subtitle at the end of this talk. And thanks for the organizing this a nice meetup. And this is the work I did in my master with my master advisor, Ernest Folkway, who is supposed to be our discussant today, but due to some personal emergency, he is not able to show up. Now let's. Okay, so I'm gonna turn into like a text mining section part first. So since this is a text analytics, text interest group and a natural language processing community, I would like to digress a little bit, talking about the history of the text mining. Myself, actually not that familiar with this history until I prepared this page of slides. So actually text mining, it comes from like 3 research areas. So it's from information retrieval, data mining, and natural language processing. So for the information retrieval, it started in 1970s and mainly about text retrieval. So for example, given a few keywords, we try to find the relevant documents from a text collection. So web search is a kind of like giant information retrieval system. And for the data mining, the traditional data mining uses like structured data. Until late 1990s, the researchers began to use text as data, which leads to the text mining. And the early stage text mining basically applied data mining and machine learning algorithm without using like natural language processing techniques like parsing, part of speech, tagging, or summarization, etc. And natural language processing itself is another whole story. It has a much longer history than the other two. So it started in the 1950s, and its objective is to make the computers understand human languages. So as text mining research kind of like expanded in recent years, it started to use natural language processing as a technique. So nowadays, text mining is kind of like a subset of natural language processing. And these kind of knowledge is from the Professor Bing Liu from UCSD. Okay, so as I said before, like a human wants to study the text, and it is easy for us to understand a document if we just given a document and read it, and we kind of can grasp the rough idea about what the document is. But how about we are given a whole library of documents? We are not able to actually efficiently process this procedure. So topic modeling comes as a way to automatically classify the sets of documents into different themes. So a form of text mining processed by David, Andrew, and Michael Jordan in 2003 is like topic modeling. And what it does is first it discovers the semantic structure and then annotate the document, then use the annotation to visualize or analyze or summarize the result. And latent delete allocation, we call it LDA. It's one of the most popular methods in the topic modeling. So it's a technique that facilitates the automatic discovery of the topics in a collection of documents, which we call it corpus in text mining kind of community. So here is a topic detection process I kind of extract from the Wikipedia. So each column is shows the document, and each row shows the term, and each cell represents the frequency a term appears in a certain document. So if initially it's supposed to be like a very messy, and as time goes by, it will kind of like cluster together and group into this kind of beautiful patterns. So in these cells, the darker the cell is, like the more frequent the word appears in a certain document. So it shows that topic modeling not only kind of like group the words that occur in the kind of like similar sets of the documents, it also group the documents that use similar amount of the words. Let's go back to the final pattern it shows. Yeah, so after this process, I'm going to show these patterns, and these patterns are the topics. So we can see that for the topic 1, we can see those terms like air, pollution, power, environmental appears in the document D0, 14, 15, 8. So it shows like maybe the topic 1 is talking about environmental science. And topic 2, if we look at those keywords, maybe we can kind of know that they are talking about maybe immigration issue. And topic 3, it's kind of like a shuttle space, launch booster. So it's probably about outer space exploration, etc. That is kind of like a general idea of topic modeling. And now let's look at LDA. So this is a very classic example from David Blythe's paper, Probabilistic Topic Models. For those who already knows this area of research may already see this example very often. I still want to use this example because it's just too classic. So this article is kind of like from Juno Science, and it's talking about how many genes does an organism needs to survive during the evolutionary time. And several words are highlighted into different colors. So different colors represent different topics. So we can see like the words organism, survive, life, they're highlighted in pink. So pink is probably about like life science topic. And the topic, the keywords like gene, genomics, genetic are highlighted in yellow. So yellow is about like genetic science. And the blue color is like a number prediction computer. So probably this is a topic of computer science. So let's imagine if we highlight all the words in the documents, except those words that doesn't contain too much meanings, like stop words. Then what we saw about a document, it's just a bag of words. And assume that we haven't read this article before and we don't know what it is talking about. So just look at those keywords, then we may get a general idea that this article is probably of the is about like a prediction of a life in the organism, the life of genes, something like that. So LDA, you kind of like use its intuition and transform it into a probabilistic model. So one way to understand it is to describe this generative process into this way. So in LDA, they assume that each document is a random mixture of topics, and each word is drawn from one of those topics. So if we look at the left side, the topics inside of each topics, they are just a distribution, kind of a distribution of the words. So if we look at the yellow topics, it's about gene science. The words gene appear like with a probability 0.04, and the word DNA appear with a probability 0.02, and the word like genetic appear maybe less frequent. And the same for the life science topic, or same for the brain imaging topic, and etc. It's just the whole word distribution in the left side. And in the right side here is the topic distribution. So it assumes that we have a distribution of different topics. So in this histogram, we can see the yellow bar seems like higher than the other colors. So probably this genetic science topics is dominant in this document. So if we draw a token from this distribution, like topic distribution, and the first we draw is like a pink token. So based on the color of this token, we come to this term distribution, and then we draw a word from this term distribution, then we draw this word life. Then we come to the second word, like we first draw a token, which comes like a yellow token, and based on this yellow topic word distribution, then we draw a word from this distribution. It becomes like a second word. Then we repeat this whole process for the whole document. That is how LDA write a document. So, but in reality, the topics are unobserved. And all we see is just the posterior. And we need to infer the underlying topic structure. So how are we going to do that? We're going to use a graphical model. So for those who are not familiar with this graphical model, here's just a very brief introduction. So graphical model is a probabilistic model that uses express the conditional dependence structure between random variables. So in the graphical model, the nodes represent the random variables, and the age represent the dependence, and the shaded nodes means the observed variables, and the light nodes represent the hidden variables. And this kind of like a square, the plate represents the repetition. So here this process repeat for n times. So I have this product of this conditional probability. The condition is like xn conditional on y, because we have this like a y token goes to this xn. So that is how we do it in the graphical model. And the graphical model for LDA looks like this. So all we see is the observed words, W. And for the observed words, it's mainly coming from two parts. First is the token. If you still remember this picture, first is the token part. Based on the color of the token, we draw the word from this term distribution. The term distribution is the beta here, and the token is Z. And the token itself is drawn from this topic distribution. So it's a theta here. And both theta and the beta, they are the distribution, so they have parameter. So they have like hyperparameter alpha and eta. So the reason we use graphical model to for the LDA is like it has some advantages. It can just define this factorization of the joint probability distribution of all the random variables, like observed random variable or hidden random variables. And it also kind of like give the independence assumption between different variables. Okay, and here is the detail of this process. So for the term distribution and the topic distribution, we use a deletion process with the hyperparameter alpha and the hyperparameter eta. And for the word itself and for the token and for the word conditional on the token, we have the multinomial distribution with the parameter theta and the beta respectively. So here's a summary of what we just did. So assume there are n documents in the corpus. The topic distribution under each document is a multinomial distribution with its conjugate prior deleted alpha. Oh, I don't know why it's. And then for the word distribution under each topic, it's another multinomial distribution with its conjugate prior deleted eta. And for the nth word in a certain document, we first select the topic from each document topic distribution, and then select the word in this topic from a topic word distribution. And we repeat this M document. For M documents, there are like M independent deletion multinomial distribution, which is the first red arrow line. And then for the K topics, there are K independent deletion multinomial distribution, which is like second line. So there are two deletion multinomial distribution happening like simultaneously in this process. Okay, after all this foundation, now let's come to the music finding part. So I realized music and text are actually very similar in the way that both of them are information carrier and emotional deliver. So let's take this Titanic tragedy as an example. When we see this news, we know it's a great loss of life, and we feel very sad and kind of very it's a very dark history of our human history. And then when we hear this song, my heart will go on, like mi fa si so fa mi do la si. You would immediately feel the great sorrow from this song because it contains a lot of like minor keys. If we use music theory to explain it. So that tricks me to think, could music deliver the information the same way as text do? And to what extent do people grasp the meaning behind each piece of music expressed by the composers? And why music from diverse culture can bring people so many different feelings? What's the similarity between music from different culture or composers or genres? And can we efficiently use topic modeling approach in music mining? So in order to make a similar kind of comparison, here's a table I made. So for the music, we have note, and it's kind of like equivalent to the letter in the text mining, because a single note like do, re, mi, it doesn't contain too much information, just like A, B, C, D in the text. So we need a series of notes that is equivalent to the word. The way we define the series of notes is like we define nodes within one measure is a word. And in the music, we know like each measure, they actually has the same duration. So one thing that distinguishes music mining and text mining is that in the music sense, the notes always have the same length. So the music words always have the same length, while the text, the word can have different lengths. And the harmony is equivalent to the topic. Harmony is like a C major, like the notes denote on the top of this music scale, like a D minor, the G major, they are the harmony, kind of like tell the key of that part of the melody. And the song is the document, and the collection of the song, which is the album, is equivalent to the corpus in the text mining. And here's a more detail of the key part, the harmony part, which is our topics. So in the music, there are 12 pitch class. So there are like 5 black key and 7 white key in the piano. So there are totally 12 pitch class. And each key, they have like a major and a minor. So they have like 12 times 2. 24 key profiles, and these 24 key profiles are the topics in the music mining. So here is another cartoon version of the music mining. So we have the topics contain all like 24 different key profiles. So for the C minor, there are going to be some keys that mostly appear in that melody, and C major, like for example, C major is like do mi so. So do mi so would have more more likely to appear than re fa la, those kind of notes. And we have these topic distribution for each song, and we can draw the token, and based on the color of the token, we draw a notes from this notes distribution, and we compose the whole song, like by repeated for many times. And that's how it works. And this is a graphical model for the music mining. It looks pretty similar as the text mining, if you still remember what it looks like. The only difference is here initially it's a word, now it becomes a note. And because we only observe the single note, while single note cannot represent too much meanings, we need to repeat it for L times. L means the number of notes in each measure. So the whole thing together represents the word. And then we repeat the whole process for n times, while n is the number of measures in each song. And then we repeat this whole process for n times. M is the number of songs in the whole album. And for the topic part, we repeat it for 24 times. Okay. And this is more detailed. It's like both the notes distribution and the harmony distribution are drawn from the deletion process, where the notes itself and the notes depend on the pitch is drawn from the multinomial distribution. And this is the mathematical way to express it. Then based on each single song, we can write the joint distribution for the whole album. And then we can write down the per document posterior. It looks like this, a very complicated form. And actually, this is impossible to directly compute it. So we need to use some approximation ways. So in my study, I used the variational EM algorithm to approximate this posterior inference. But there are actually many other ways, like you can use skip sampling or factorization inference or a stochastic inference, etc. There are many ways developed since the topic modeling become very popular. And for variational EM algorithm, we, instead of like directly doing this, we transform it into a simple way, just like this. So because this one is more easy to compute, they're all kind of like independent with each other. So we can write these graphical model down into these forms. So we call it Q. So we use this Q to approximate the initial P, and we want these two distribution kind of like as close as possible. So we try to use Kuba-Leiber divergence to minimize the distance between the two distributions. Okay, that is a whole theoretical part of it. And we also looked at the audio music models. So sometimes we wouldn't have the music sheet, like improvisational part or solo part. We only have soundtrack. So in that scenario, we wouldn't observe the notes. All we observed is the thing called a corona vector. So this corona vector can kind of like can extract from the soundtrack, and we assume it's from a Gaussian distribution, and we use this corona vector to infer the hidden notes. So that's the only difference between the audio music model and the sheet music model. And now let's compare the two models, the text mining and the music mining. So the difference is like the note part, while the note repeat for L times. And in the mathematical model part here, instead of using the word, we have X, which is the indicator vector with a series of notes like from certain pitch kind of like noted. And the Z is the scalar from 24 key profiles. And the model comparison for the symbolic music and the audio music, we have this extra part to infer this note. And the mathematical model part, we have this C here. The probability of the corona vector is from the assumption of Gaussian distribution. And also, actually, it's not necessary to use Gaussian distribution as long as you think some certain distribution makes sense, you can probably try it. Okay, let's come to have a look at the implementation. So there are many different music genres like in the world, like pop music, Latin, country, hip hop, rock. So previously, some researchers, they studied the classical Western classical music, like Diane Hu and Lawrence So from UCSD. And actually, we consult them in this study, and they help us a lot when we're collecting the data and when we discuss the methodology. So in their study, you can see here's one of the results from their study. So here's the key judgments from the first 6 measures of Bach's prelude. And the top part is the result from LDA judgment, and the bottom part is the judgment from the human expert. And we can see the LDA result and the human expert result are pretty close, which is pretty good, the result. And now, so we decided to study jazz because jazz is pretty kind of flexible and dynamic. It contains a lot of like solo part and the improvisational part. So although it's very flexible, but it still follows certain music theory. So kind of like it has more kind of variation inside of it. So we are not sure if LDA can handle it properly. So we mainly collect the data from 6 jazz musicians' songs. They are like Duke Ellington, Miles Davis, John Coltrane, etc. And I manually kind of like processed it. Basically what I did is I download those music sheets in the MXL files. Then I transform it into this matrix form. The way I transform it is like based on like the certain duration of each measure, we can create the same kind of number of columns in each row. So for example, the first measure is fa, do, la, mi, do, la. So fa and mi actually the twice duration than do and la. So when we transpose to here, translate here, we write like fa, fa, do, la, mi, do, la. So, and the same for the next several measures. So we can transform the whole sum into this matrix form. And if we have a collection of sums, then it becomes a tensor of matrix. And here's some result from these topic models. Although we still need more kind of like interpretation and insights from the musicians, but here we at least can see in some topics, it's very messy with a lot of like sharp and flat keys. Those sharp and flat keys are like black keys in the piano keyboard. And some of the topics are very pure, only kind of like mainly focus on the white keys. And some of the topics are very kind of like contains a lot of different notes or music words, while some are very sparse. And yeah. And here's another result from about the relationship between the topic and the musicians. We can see that the musician like Sonny Rollins and Louis Armstrong seems to contribute a lot to the topic too. So probably their music kind of style are similar, or at least based on the music songs I collect, their music styles are very similar. And John Coltrane, he contributed a lot to topic 6. And also we can tune the parameter to go into further detail of it. And then we actually jump out of the jazz genre kind of circle. We look at the whole different genres and collect some American music, Japanese music, Arabic music, and the Chinese music. And what LDA tells us, it seems like American music contribute a lot to topic 9, while Arabic contribute mainly to topic 3, and Chinese music contribute to topic 4 and 5. And the Japanese music seems to just spread out everywhere. Maybe many focus on 10, 11, 12. And here is the audio melody tracking about the beat. So I plot the like 16 beats about how the tonality changed as time goes by. So if you look at this torrid shape, you can see the local tonality initially focused on the A major and the B minor in the first beat. Then in the second beat, it goes to the A minor and E minor. Then it's kind of like a sweet shift to like F major. Then as time goes by, it goes to like B minor, E minor, then back to A minor. If we look at these plots, it's maybe more clear. Like this is how the kind of like a tongue switch as time goes by in this song. So, okay, here's what we did, and we studied this harmony and knows that the harmony could be learned by the topic modeling in the music space. And we're actually wondering how accurate could human emotion hidden in the music be detected and extracted through the probabilistic model. And we also like want to explore in the future that the improvisational key, like how many keys do the jazz musicians tend to play and what are those keys? And also the musical harmonies and its connection with the elements of the mood, how we can kind of like deeper understand those mood elements. Also, apart from the notes, can we embed other inherent music structure like cadence or tempo to better interpret the music words? And actually during this study, we kind of like projected the music sheet into a bag of music words, and we consulted a lot of musicians and music lovers. They all kind of give us a lot of useful suggestions and positive feedback. So we call it like a naive dictionary now, and in the future, we want to kind of build a complete dictionary of music words. Okay, now let's go back to the initial, my subtitle, text mining and music mining, an eternal golden braid. Because I was kind of reading this book recently, and you know, the Godel, this book is kind of like a famous book, win the Pulitzer Prize. And the Godel is a mathematician, Escher is an artist, and Bach is a musician. But Godel's kind of, he has a famous statement says like this sentence is unprovable, which means this sentence is not true. Well, if this sentence is not true, itself is actually true. So it's kind of like a self-conflict or self-referential. And Escher's kind of pendings is also, I bet you also all like saw that pending before, like it's like all the stairs interconnect to each other, and if you look from different angle, it will kind of like maybe coming from different parts. Or another example is like within a pending, it's a pending itself. It's just like within a mirror, it's a mirror itself, like many other mirrors. So it's another way of self-referential. And the Bach's music is like it goes from very low key, then up to the very high key, then it go back to the low key, then kind of like in a looping style. And actually not only Bach, there are many other sampling music like a hip hop. So they all kind of like reference their own music within the music. So although this book is saying that although they are from many three different fields, but they kind of use similar kind of philosophical ideas in their own works. So I feel like statistics is like an eternal golden braid that bridge the text and the music, and they three, although they kind of from three different fields, but they are interconnected with each other. And that's probably one of the reasons that attracted many eyeballs, and probably one of the reasons you guys are sitting here now listening to me. Okay, and I thank you so much for your attention, and I'm open to any questions.
Thanks, Queenie. That was great. I did see a couple questions in the chat, and I have a couple of my own. The one I saw in the chat was, can you talk more about how people classified the music genres, and how do we know that those, like, could there be any human error introduced in those classifications?
Human error introducing these classifications?
Yeah, like when you were comparing the human to the LDA.
Oh, you mean how the human expert's judgment comes from?
Yes.
Yeah. For the Western classical music, I feel like the error probably is minimized because I talked to those musicians about, like they told me they studied those series and like and especially in those classical music, it's pretty rigid to follow the certain rules. So the answer would be kind of like unique. If it's just C major, then it would definitely be C major. But if it comes to like a jazz or other sort of more flexible music, probably the human judgment can have some error, and it's also depending on the experience of the musicians. If he is more kind of like young, or he maybe made more errors, or if he is more experienced musicians, maybe he can kind of like has less errors. Yeah, and LDA is kind of not based on the experiments, right? It's based on the training data. If you give him more data, so then maybe he would give you more like a better result. Yeah, thanks. That's a good question.
Gotcha. So another question that just came in, can you explain the matrix that you have on slide 36?
Yes, the data matrix. So this 6, okay, here. Okay, yeah, so explain again. So yeah, so in the music, each measure, they have the same duration. So it's gonna have the same length. So each measure is one row. And the second measure is the second row. So there are totally, I guess, like 12 measures in this song. So we have 12 rows in this matrix. And if it needs some requirement, like understand the music sheet. So in the music, it's like fa, do, la, mi, do, la. So this is twice the duration of the second and third notes. So in order to make it the same length, I read it double the time because I want to make the duration of each note the same. So I read it like fa, fa, do, la. Is that how, did I explain it clearly?
I understood it.
Yeah, we also, oh, by the way, we also denote the rest part because in the music we have the rest, which you don't play any keys. So I denote it as O, like letter O, and the do, re, mi, fa, sol, la, si is like a C, D, E, F, G, A, B. Yeah, denotes in this letters. Yeah.
We've got a bunch of questions coming in, so I'm going to selfishly put my question on the front of the line.
Okay.
What tools did you use for this analysis?
Oh, in this, when I extract data, I use R to kind of like wrote piece of code to transform it into the matrix. And for LDA, I also use mostly I use R. And for the later part, the audio soundtrack, the tonality part, I use MATLAB. There's a person developed a toolbox called a MADI toolbox, and it's very powerful. It has a lot of useful functions. So I use MATLAB to process the audio soundtrack.
And which packages did you use in R?
Oh, I think LDA, or it's most commonly used with LDA. Yeah, okay. I guess it's LDA. Right. When I visualize it, I think I use this kind of package, the circle license by this guy, because I feel this plot is very beautiful.
Gotcha. Yeah, no, they're really pretty pictures.
Yeah.
Okay, so back to audience questions. Can chords provide further information on repeatable patterns besides the notes alone? So I guess, could you look at a
You mean-
chord as like a single token for the analysis?
That's a good idea. Chords itself as a token. Chords itself is a token, right? Because when you say chords, it means like the harmony. Is that so? Yeah, if it's a chord, I mean, in my definition, I say harmony is a key profile, which I would kind of like refer to it as a chord. So chord itself is a token, which is a topic. Yes, the answer would be yes.
Gotcha. And
Yeah.
how do you interpret silence in the music where there might be gaps?
Interpret it.
Or I guess, how did you handle it in terms of modeling? Did you ignore it?
Oh
or did-
yeah. I said it as I said it as O here. So in the result, you're gonna see there are some. You see this O here. The topic is totally silent. But if actually later we discussed with the musicians, they would interpret it as kind of a rest. Or like when you write a kind of like a text article, you have like a big like a period or like a big silence. So it's kind of like when you are rest. So that is how we interpret it.
And where did you get your data from?
Oh, there's a kind of software called the MuseScore. The MuseScore itself is not for any of data science thing. It's just for the people who learn how to play the piano. So they have millions of the music sheet in like a piano sheet. Then you can download those sheets in these MXL files. So I just pick the targeted musician songs and download all those files and transfer it into the matrix form. Yeah, it's from MuseScore. It's like MuseScore. Yeah.
MuseScore. And here's a sort of an interesting one. How do you envision approach to mapping the topics to sort of like a music summary? So like a description of topic mapped to human emotion. I guess what they're meaning is sort of like how with LDA for like words, you would look at the words in the topic and say, oh, this must be about cats. How do you make those sorts of interpretations with music?
Right. So that is a little bit beyond our like a statistician or data scientist kind of knowledge scope. So I indeed need to consult a lot of musicians to help me, like give them my running result, and help ask them, do you know what it means? And do you know how we can interpret that? So they're gonna look at those translated notes, and they're going to tell us maybe these parts, because they gathered a lot of C major kind of notes, then it's probably like excitement, and that part maybe gathering a lot of like minor keys, so it can have a little bit sad feelings or things like that. That's how we currently interpret the result. It definitely needs to improve.
Somebody's asking about if you've thought about using this model maybe to like build a recommender system. Like if you like this music, surely you'd like this. So like comparing similarity of songs.
Right. I've seen there's some literature using LDA sort of like do some prediction, so which is part of recommendation system. Yeah, you can definitely do that. Yeah.
And another question about I guess that's the matrix that's up now. Does the measure note matrix or the feature representation models the same chord with different octave? So I guess they're asking if it's, I think that might be a question about maybe like the columns of the matrix. Are those the same chords with different octaves? I also don't know anything about
Mhm.
music, so I could be butchering this question.
Yeah, actually, not fully understand this question. Can you say that again?
Sure. Actually, I would ask if Jeff H, maybe can you rephrase it so a dumb non-music guy like me can repeat it? So for the visualization that showed the relationships between musicians and topics, what calculation did you use to determine the strength of that relationship?
Oh, in the LDA, they're gonna show you the probability like of certain nodes. They're gonna like kind of gather what kind of like musicians they also have that sort of like that sort of style, then connect them into it. It's actually based on the probability. So each of the connection they behind the scene, they have those probability kind of like numbers behind it. So the stronger it is, the like the thicker those kind of string looks like.
Oh, got you. So this was
They have
got you. So that's just the strict posterior probability. It's not like a distance calculation or anything like that.
Oh, I understand your question now. Yeah, I think it's a calculation of the posterior instead of the distance calculation. But I need to double check it. I'm not fully sure. Yeah, it's a little bit, yeah, long ago.
Gotcha. So I think the last question that I have, although maybe if I missed something, type it in the chat again. Do you have any thoughts on rhythm, especially in jazz?
Any thoughts of what?
On rhythm? So like maybe how you would model rhythm, like in jazz?
That's a kind of an open question. Yeah. So currently, jazz is still a challenging field, I would say, even we are kind of trying to do it, but I wouldn't say we successfully kind of like finished this part. So we're still exploring this. Yeah.
All right, great. Well, I think I don't see any. Oh, nope, just came in. The same C major chord may have different scales, high or low, or use different keys. Does your model treat them as the same?
Right. I think I consider this part, and in this study, we consider them as the same. We group even higher and lower as different, as the same. And actually, in my future direction, I mentioned that, so we can treat probably different, like a high key, low key, as a separate. But if we treat them separate, I actually don't think it makes sense, because it would be more spread out. So it's kind of like a word, but it's like a word like with similar meanings. So it's probably we're gonna still group them together. So yeah, so we treat them together. The short answer is.
Sure. And
Okay.
William was hoping to unmute to ask you some questions.
So
go
hey,
ahead.
Tommy, Tommy and Chiu-Ying, thank you so much for the presentation. So I do have a couple of questions on the practical level. So I mean, I know the text mining, so basically like a language processing, there are a lot of use cases have been applied in the real world. So, but for the musician, like for the music mining, what kind of business value it can be derived from this kind of musician mining? And would you be able to like recommend a couple of like kind of a business use case, especially for the music mining? So because we know that text mining is more, it's right now is pretty popular in the real world. Even in my own project, we using some transformer data to text mining and transform the requirements into different like documentation and for the data architecture or modeling. But for the musician mining, is there any particular like a business use case, and what kind of business value can drive from this kind of like the study and the research? So that's one to understand.
Yeah, so a very good question. So one of the mode that actually already used in the business nowadays is the recommendation system that I already mentioned by some other people before. So we indeed use it in the recommendation system, and almost all the like music app are using this feature now. And we also can kind of like use music maybe to detect some music, but it's more about like science use, to see how the brain is like a cognitive science field, how the brain's kind of nodes are kind of like reflect as we use different sort of music. Yeah, so one of the business model that now come to my mind is the recommendation system. Yeah.
Okay, you mean recommendation system is recommend the people, the consumer, to buy some like albums they used to is try to figure out the pattern, the pattern of the music they favored, and they then can recommend some of the new albums which you like
recommend a similar song to
correlated to their interest and the kind of a favorite pattern, right?
Right.
Okay.
Right.
I see. Okay. I see. This more up to okay. So yeah, they could be like expanded a lot. But the second question is about the framework. So right now, the Python is very popular like a language for machine learning data science, because they have some like a very very popular like a sort of framework such as Keras, PyTorch, and the TensorFlow. But you mentioned that you are using R for this musical mining LDA. I don't know too much about R, but I know R is kind of a statistician used and the MATLAB. But what's the main reason you're using R over Python? Is it because just it has the music mining that kind of libraries which Python doesn't have, or some other
right reason? I mean, Python definitely is very powerful, and those machine learning kind of algorithm like a package you mentioned are all very like maybe more powerful than the R. It's just because in daily life, like statisticians are using R. So, and this study is not using like a huge amount of data that are just gonna be crashed. So it's just a very small amount of data, so we can use R. It's just more convenient for me. So if in the future I want to put it into the business mode, I would definitely transform it into like a TensorFlow or Python, or like the other more advanced language.
I see.
To large scale producing it.
So from your side is more on the like
actually, hey William, sorry, you've had a couple questions. I still have some folks in the chat, if you don't mind.
Sure. Yeah. Okay. Yeah, I'm good. Thanks so much for the answer. Yeah. Thanks. Okay.
Yeah. Thank you.
Thanks for the questions.
I did miss a question before. I think this is similar to an earlier one, but have you looked at anything like n-grams in text? So like analyzing 2 bars at a time, or only 1 bar at a time?
Right, that's a very, very good question. Yeah, that's one of the difference we didn't do in the music mining, because as you see, each kind of each song is so small. At least the song I collected, they are just a little kind of matrix box. So if I connect those in like some notes, some music words together, then it's gonna be just super short. Then we don't have enough data to kind of generate some meaningful result. So in this study, we didn't do, it's just one gram. But yeah, definitely if there's a kind of like a super long music, then we're gonna do n-gram. Yeah, and in many text documents, we always do n-grams because it's more like reasonable to do that.
All right, and one more question. I'm gonna call it the last question of the evening. You're very popular, Chewy. Have you ever seen anything that is like a sentiment analysis based on notes? So sort of going, I guess, the other way.
Oh, sentiment analysis based on notes, I didn't see, but I've seen literature about sentiment analysis based on lyrics. So that is the thing we want to study, but it requires a lot of knowledge about music. So you need to be very familiar about each note, or those several notes that represent certain kind of, as I say, like C major, which is do, mi, sol, usually gives you a very
Great. Well, thanks so much, Shui. This has been a great talk. We're really happy to host you. And
thank you so much
again,
for the invitation.
Both the text analysis interest group in the ASA and latent Dirichlet allocation are very near and dear to my heart personally. So very excited about all of this. All right, thanks. Bye, everyone.
Yeah. Thank you. Thank you so much.